Okay, so today I'll be giving my presentation on a bit of a tutorial working with the Iron Mind project. We recently put out a preprint on this work, and it's primarily looking at large language models as chemical reaction optimizers and comparing with Bayesian optimization. So where this aligns with CCAS is primarily as an optimization algorithm, although touching on some other parts, but primarily in the algorithms theme and optimization thrust. Yeah, and then as I mentioned, we put out a preprint on this project recently. This is just to let you all know that that's out there. And now I'm just going to go briefly over what is chemical reaction optimization, what is the challenge therein. So chemistry experiments require optimizing multiple parameters across complex multidimensional campaigns. So we have multiple inputs, and in many cases, we also have multiple objectives which we're optimizing over. And the current reality is that we have advanced methods like Bayesian optimization, which work uh, fairly well, but can struggle with categorical parameters. And it's often somewhat related to the previous presentation with not being able to represent those adequately and what is adequate changes based on the problem. So the dilemma sort of is, can artificial intelligence, primarily large language models, transcend these mathematical constraints by leveraging some pre-trained chemical knowledge and intuitive reasoning skills? So sort of just on like the timeline, where we started with this chemical reaction optimization is basically just based on chemical intuition, just picking parameters to test that we thought would work and going from there. Then we got a bit more mathematical with it, with maybe one factor at a time optimization, and then design of experiments, breaking things into levels, and optimizing that mathematically. And then Bayesian optimization, which allows us to balance exploitation and exploration of a larger parameter space, but again, in a very mathematical way. And then in this work, we introduce some LM guided optimization, which takes your chemical reaction problem in terms of the substrates, the parameters that you can tune, as well as the procedure that was carried out, and give that to an LLM to get suggestions of what conditions might work well and do that in an iterative fashion with in-context learning. So to sort of see how this LLM guided optimization performs, we benchmarked against Bayesian optimization. And sort of at the top here is what these optimization strategies look like and what we get at each iteration. So we just start with some data set, and this could start as empty or just a few experiments from a given parameter space. And we can do GP, Gaussian process-based Bayesian optimization, where we get our surrogate model, our acquisition function, and together these give us suggestion of parameters, which we observe and then send back to the data set. For the LM guided method, or how a human would carry out this process, we get both a suggestion of parameters, which could be a batch of parameter suggestions as well as reasoning for each of those selections at every iteration. So why those are to be tested, is it to test some hypothesis that's a negative or positive hypothesis? That's something we don't necessarily get from Gaussian process-based Bayesian optimization. So a key differentiator there. And then just our generalized optimization algorithm, we have our objective function, right, which could be something like yield or selectivity of a reaction, batch size, so the number of experiments we're going to run each iteration, and a budget, which is the total number of experiments we're willing to run to get good results from this reaction. And every iteration, we just suggest a batch, observe it, and then do a subsequent suggestion. And with our LM method, as I sort of mentioned, we have our substrate pairings, our conditions, as well as maybe some procedure information, which all automatically goes into a system prompt for the LLM. So it gets information about what the tunable parameters are, what the options for those are, the type of parameter, be it categorical or discrete, and then also some general guidelines, what the batch size is, so how many suggestions it will be making, and then if available, which in most cases should be available, some more context about the exact experimental procedure that's being ran, as well as the analytical technique in the whatever case it might be. So we benchmarked this by doing 6 large language models from Anthropic, 6 large language models from OpenAI, 6 from Google or Gemini, and then we use 6 baseline Bayesian optimization strategies, so 3 different acquisition functions, each with and without descriptors, And for this, we use the Atlas package as our sort of engine for the Bayesian optimization. And first, just go over the data sets that we ran this benchmarking across. So it says 6 diverse chemical reaction data sets. We actually did 7, but in the paper, we only present results for 6 of them. But on our web app, which I'll open here, you can see all 7 data sets, which we have results for, and you can look at them in more detail. So it'll tell you the size, so the total number of experiments that are contained within that data set, what the parameters are, and the objectives, if there's multiple. And then a distribution of the objective value as well for each of these. So we have one multi-objective data set here. And then you'll also see that there's some information about a description of the data set. So this really contains what the procedure was like. And for this particular data set, I actually extracted it from ORD to get the fully mapped set so that we could use it as a benchmark data set, and basically just took the information there and put it in as a string for the description of this reaction. So it has all the sort of metadata that's present on ORD for this particular data set. And then we have our 2 different objectives and what their distributions look like. Yeah. So in total, we have 2 Suzuki coupling reactions, one that measures for conversion and one that measures for yield of the product, a Buchwald-Hartwig reaction, a reductive amination, an alkylation deprotection, and a Chan-Lamb coupling data set. Oh, as well as an amide coupling, not shown there. Yeah. So the first thing we can do is, so we ran 20 campaigns for each method with a budget of 20 experiments and a batch size of 1. So just serial optimization up until a budget of 20 in 20 independent runs. And the first thing we can do is just look at the performance of the different methods across these data sets. And what I have shown here is basically, so across the 20 campaigns, I just get the best objective value from that campaign and then plot a box plot for the distribution across each data set. I'm just going to reveal all the results here. So it's color coded based on data set in a particular order, which I don't quite have the time to get into in this presentation. But what we can see is that the LLM methods are quite competitive with Bayesian optimization across a number of data sets, and for some of them even performing much better than Bayesian optimization. The one real main outlier is the Chan-Lamb data set, where we had multiple objectives as well as multiple measurements per parameter suggestion. And we see that Bayesian optimization does better than the LLM there. But, this is only one way to sort of compare the two via their performance. But what another aspect we're a bit more interested in, or we think is also equally as useful, is to sort of interrogate the reasoning that we get from the LLM method as to why it's suggesting certain experiments at certain times, and do some comparative analysis with what humans would do in a similar optimization campaign to really assess essentially the trustworthiness of LLMs in this sort of like scientific endeavor. So for that, I'm going to turn over to the web application that I built to sort of allow people to work with these data sets and get an idea of how the LLM and Bayesian optimization methods work, as well as help us collect some of that data for comparative analysis. And that's sort of where I want to give the tutorial for this part, just to show you all how you can help us sort of gather this data and also challenge yourselves with these data sets. So first I'm going to log out. And the first thing you'll have to do when you visit the website will be log into your ORCID. This is how results will be logged back to you as the human. And the first thing I'd encourage everyone to do is sort of take a look at the leaderboard. So this leaderboard tells us for each data set what the best performing methods were on that data set at using these pass at K metrics. So pass at 3 means just what's the distribution of best objective values across all the campaigns run for that method from the benchmark after 3 experiments were observed. And then 5 is pass at 5 experiments being observed, and then 20 being the full budget. And we can look at this in median mode, where the bars are the median of all those best objective values across the 20 campaigns. And this green is the best objective value, and red is the worst best. And we can look in median, where the line is now just the median. And then for each data set, we can go down to the table and sort at these different pass at K metrics to see which methods turned out to perform the best. Right. So we can also look at some of our collaborators already did some human runs for us to put in the preprint as sort of like a guide on how to carry out these. So I'll do an example of the human run, and then I'll publish it and show how that's done. But once it's published, you can look on the table and you can click on like a human run, and you can see, in this case, it was Jeffrey Ethier from AFRL who did this run. They selected their conditions, saw their objective value, and they, oh, sorry about that. Oh, and you can see their reasoning for why they ran this experiment, and they just go through doing their reasoning. So now I'll go show how one of these runs is actually generated. So I'm going to do mine on the amic coupling data set, and I'll just call it test run, and I'll just keep it kind of brief. I'll do a batch size of 1 with 4 observations. And yeah, so now we're on the optimization interface, where we can start evaluating different experiments for this data set. And all the data that we see will be from the literature data set, according to the paper that this came from. And yeah, so first we have the data set overview. All of this information is something that the LLM would see, so we're also allowing the human to see it. And it just gives an overview of what the parameter space looks like. So we have 3 amines, 3 carboxylic acids, and 72 curated reaction conditions. And importantly, with this data set, the condition parameter is a set of conditions. So it's a set of activator, additive, base, and solvent. And in this case, the same solvent was used for every reaction, opposed to being fully mapped across activators, additives. Because for this amic coupling, it makes sense that we wouldn't use an additive with all of these activators. Not all activators are typically run with an additive. Some activators require you use an additive. So that's sort of, that parameter is consolidating all conditions into a given set. Yeah. So now we can go down, and this will tell us what the objective value distribution is for it, just to give us an idea of how difficult this might be to optimize, and what we interpret as success based on what the distribution looks like. So first, we're going to select an amine. So I'm going to start with this benzylamine, and then the phenoxyacetic acid. And for the conditions, I'm going to do just a particular that I know is a well-validated set of conditions. It's this one. A4, 7. Okay. And yeah, then we can look at actually what the structures are. So this is R8 is EDC HCl. The additive is HOBT. The base is DIPA, and the solvent is constant for all of them. So I'm just going to start with that, and the reason I'm going to do it. So now that I've selected them, I can put in my reasoning for why I'm running these experiments. Nation. And then I picked this benzylamine because it's rather nucleophilic. Good. Okay. So I put in some reasoning, sort of trying to follow these guidelines of analyzing previous data, hypothesizing what factors are critical, and providing rationale for why I picked this. And then I just go ahead and hit submit parameters. And now I'll get back the yield for that experiment. So 50%, it's about what I kind of expected. The experiment should work well, but not the best. So it's pretty mediocre, right? Um, so now let's make a modification. Let's stick with the same amine. Go with this third acid with the group over here that might make it more reactive. And then the same conditions, just to see if we can get a better substrate pairing for this. I'm just going to keep it brief to keep this sort of moving, but you can be more detailed, less detailed. Any sort of reasoning that makes sense is useful here. Okay, yeah, so we get a jump in yield, and now we can run another experiment, maybe to look and see if a different amine with the same acid and same conditions will perform just as well, a lot worse, or a bit better. Right, so I'll just leave this for now. So we get the yield goes down quite a bit, so we should probably just stick with this substrate pairing and try to get that reaction to work as well as we can. So maybe we could do a different base in our conditions. Right here we have the 2,6-lutidine. And again, and then for each of these, I also have a checkbox here for you to say whether or not you maybe did some research when looking into this, which you might cite in your reasoning specifically, and then like how much time you may have spent doing that. So that's not necessarily prohibited in this process. It just needs to be marked there as such to give a to allow us to compare with the LM reasoning as well. So for this, I set the budget to be 4 experiments. So now that we did the 4 experiments, it asks if we want to return to the optimizers to maybe do a different data set, or if we just want to look at our results. We'll just look at our results, and we can see a plot of the results over the iterations. And then, yeah, at this point, we can publish our human results to the leaderboard to see where it stacks up in comparison to the benchmark methods. So once we hit that publish button, we go straight to the leaderboard, and we have the amide coupling HDE dataset, and we'll find myself here only with a pass at 3 metric because I didn't quite do 5 experiments, but we can see where that stacks up compared to the other LLM methods. Yeah, so I think that kind of concludes my tutorial. I'm happy to answer any questions.